Lab 6 has us looking at the two-stage CMOS op amp. So it's the same thing as Lab 5 for the first half, but additionally we're going to add this second stage, which has the common source PMOS with the load RD, which you figured out from the pre-lab, and some load resistance. So it's not much. For the hardware and for the simulations really, we can ignore this voltage divider stuff at the input along with this 100 microfarad cap. You can apply the input signal directly into the gate here. So that'll simplify things. The input will be a 1 kilohertz sine wave, and it'll be very small. We'll probably do 10 millivolts amplitude or 10 millivolts peak to peak, something along those lines. So the hardware is the same as Lab 5, essentially. You don't need any more components besides the few resistors that we add. The PMOS that I'm using on the current mirror chip up top. So the bottom left hand corner of that chip is what I'm using for the current source, or not the current source, the common source amplifier for the second stage. So those bottom three drain gate source connections are added now. So the output of the first stage, where the NMOS and PMOS drains meet, that's going over on this yellow wire to the gate of the PMOS of the second stage. The drain is going out to the output node, which is also connected. I put two resistors in series, and that goes to the minus 5 volt supply, and that's my RD. There's also the capacitively coupled output resistor, and that's connecting to ground, that resistor. And also on ground I have the negative scope probes for reference, the references. The black wire from the analog discovery for ground, and also one of the inputs of the differential pair. So my right hand side differential input is going to ground as well. Similar thing as what we did for Lab 5. But other than that, the circuit is the same as what we just did for the previous lab. So I'll kind of go around a little bit, try to zoom in so you can see what I added here. I don't know if that helped. That capacitor is connected to the resistor, and that goes up to the side here. There's like a hair on the board. Gross. And there's the PMOS inputs up there too, for the common source second stage. Okay. So if I go to our lab document here, Lab 6 data, doesn't have us collect much information. Refocus. We do have to measure the output current, the second stage current, and V out DC. What is I out? I think I out is just asking for the measurement of the output current of M6. I second stage is the current through the second stage, current flowing through RD. So if we measure the voltage drop across RD, and you know what RD is, then you can figure out the current pretty easily. And V out DC, you're going to measure anyways in order to figure out that current. So it's just the DC voltage at this node. And then we need a picture showing the hardware along with a scope picture. Now I've already got the scope running for this, so I'm gonna grab that first. So I've done a 5 millivolt amplitude, 1 kilohertz sine wave. So peak to peak 10 millivolts. And you can see that on the scope here, that's the yellow signal. It's pretty small, so it's hard for the scope to trigger on it because it's pretty noisy. And blue is the output, which also looks kind of noisy. But you could export this data and figure out what the differential gain is from this plot. And for me, it's just ballparking it with all the noise. It looks like the output swings about 1.5 volts. And if the input is 10 millivolts peak to peak, then the gain is about 150. So a little bit higher than what we simulated or planned for. But still ballpark kind of close, I guess. So that's the picture that you could put here, along with your hardware picture once you have that, and just calculate what the differential gain is based on your data. The other piece to this is measuring the DC voltage at the output to make sure that that's correct. And you could do that by, I think I'm already probing there already. No, I'm probing on the other side of the cap. So you just want to make sure you're measuring where RD is. And this is currently measuring to ground because the negative side of my channel 2 is going to 0 volts. So if I go over here and look at the voltmeter, run that, and I'm looking at channel 2 right now. It's minus 200 millivolts. So V out DC is minus 0.2 for me, and you can use Ohm's law to figure out what this current is here. And that's it for this lab. Pretty simple as long as you get the hardware set up correctly, which will be most of the effort.